All right, so the things up here that we know are the hypotheses. The thing we're trying to prove is the conclusion. We're safe assuming the hypotheses are true. That's why they're called hypotheses. So we can say not Q is true. Everything you write in this proof must be true. Because our ultimate goal is to be able to write a statement that just says T, right? And if everything follows from things above it that are true, or from these rules of inference, these implications and equivalences, then everything we write will be true. And if we can eventually write T, that proves that T is true. That's the basic setup. So we can write not Q, but we have to say, why is that true? It's true because it's a hypothesis, right? All right, so second step. Well, we had this insight perhaps that since P implies Q and Q is false, that's going to make P false. Okay, but we need to formalize that. We've got P implies Q and we've got not Q. So let's go over here and look at these implications. And which one relates to P implies Q and not Q?
Indirect reasoning?
Yeah, it's actually using the same letters even, which is extra nice. So indirect reasoning. So let's write down what we're going to use and say that's a hypothesis. All right, so we've got to write down P implies Q. But now, if we take this, number 2, and we combine it with number 1, using indirect reasoning, we'll be forced to conclude not P. So the reason is indirect reasoning. And say which things you're putting together in that, 1 and 2. So we have not P. We're going to combine it with P or T. So let's put that down. That's a hypothesis. Okay, so the claim is if we have P or T and we have not P, then we must have T. What's the reason for that?
We've proven that not P, but
Direct reasoning of 3 and 4.
So about half the class said direct reasoning. This is not direct reasoning. Direct reasoning says if P implies Q and P is true, then Q is true. They call it detachment, but it's also called direct reasoning elsewhere. But what's going on here is we have simplification. So we have P or Q and not P, that gives us Q. Or if we have P or Q and not Q, that gives us P. Right, so if you know that the or, either this is true and this is false, this has got to be true, right? So that's disjunctive simplification, right? Disjunction is the or and we're simplifying. So this is disjunctive simplification. And it's using parts 3 and 4. Do we have to prove anything after this? We just proved T, that's what we were trying to show, so here you can say QED. We just proved T, which is what we were asked to demonstrate. Okay, so let's go indirect. So indirect, we start off by negating the conclusion, and we try to argue to a contradiction. So step 1, I'm going to say not T. That's not a hypothesis, that's an assumption. And it's the only assumption we're going to make so that when we get a conclusion, we can say, okay, that assumption must be erroneous.
why do we call it an assumption instead of a hypothesis?
Because a hypothesis is something that we know is true. So if we're saying that not T is true, how does that help us with any of this?
Disjunctive simplification?
Again, disjunctive simplification. So we know that P or T, and that is a hypothesis. But if P or T is true and T is false, then P must be true. So that's disjunctive simplification of statements 1 and 2. So what do we do with P? Let's hear from this side of the class. We know all of these hypotheses are true.
So you can say P leads to Q,
P leads to Q.
and
That's a hypothesis.
Since P is true, Q must be true.
So therefore Q must be true. And the reason for that?
that one's direct
That's
reasoning.
true.
That's direct reasoning.
But Q is false. So then you have a contradiction.
Q equals not Q.
So here's where we can be a little tricky. We've shown that Q is true, but we also know that Q is false. That's a hypothesis. So at that point, I'm okay if you say contradiction. Okay? Or if you want to be more wordy, you could say Q and not Q. Right? And that's the definition of conjunction, I guess. And Q and not Q, there's a identity which says that's equivalent to false. Right? So Q and not Q is false, so that's a negation law. And once you've got false or zero written down here, you can say contradiction. But I'm okay once you've got Q and not Q right above each other being true, I'm okay if you say contradiction. That may not need a number. I don't care, it's up to you. So there's a contradiction, therefore, 3 dots means therefore, T must be true. Right, so once you reach a contradiction, you can say your assumption must have been wrong, so T must be true, and now you can say QED. If you write QED right here, after not Q, you're claiming that you were asked to prove not Q. That's not true. If you write QED right here, you're claiming that you were asked to prove that there's a contradiction. That's not true. You were asked to prove T. So the last thing in your proof should be T. And then you can say QED. Make sense? These didn't cost you points. I'm just pointing these out for completeness. What did cost you points is if you didn't have reasons down here, okay, if you were going through the right steps and I kind of saw the right statements, but they weren't laid out in a clear sequence where you do this and then you do this and you put these together and so on, right, that cost points. If you did something just plain wrong, if you said not Q, P implies Q, therefore T, right, and there's some missing steps there, that cost you points. And if you didn't do the problem, that cost you points. But I made more comments on your proof than I took off points for, basically. But this would be a nice, clean presentation of that. So, so we're going to be doing proofs all quarter, okay? But kind of starting from this, are you getting the idea of how to do these things, right? Dotting I's and crossing T's aside. Do you want to do one more on the board? Sort of nail this down? Okay, let's do that. So this is for a all right, so let's take 10 minutes and see if you can do direct and indirect proofs of this at the board. on lights. I can't see the board. Never mind.
Say use direct reasoning.
Well, what first step stating non-given? Said direct and indirect.
Oh,
So those three things that are given.
Are given one, and then
this is our
not R is true, then not Q is true.
Where's the
if not R, then not Q.
We're about to use it.
even Q?
Direct reasoning.
Because you have to work out to it. So like the very next step is to work out to P then Q.
Okay. Then you'd say that's an assumption.
If P then Q, and since not
You could put that
P
in
or
the
Q is not, so P
Well,
also be
You
false.
could do it, but it flows better.
Because now you can
Logically,
I think you need to state not R and not Q as step number 2.
therefore
We know Q is
can't
true.
be true. Because
How do you know Q is true?
That's given.
I see. Because these two are.
If P is true, then Q is true.
These two
Can
are
you immediately say that's based on
that we very Yeah.
The direct reasoning would say if P implies Q and P is true, then you can say Q is true.
Not Q. That's what we're trying to say.
I think we'd state P then Q.
Now, indirect reasoning is true. You want this one?
Okay, you do it.
Disjunctive simplification.
I think it might be, but I don't know my.
Yeah.
I don't have my reasoning, just based on what he said earlier.
I would say like just say disjunctive simplification.
It still makes it
So we're gonna, since it's indirect, we're gonna assume the hypothesis. So we're assuming P.
This is 2-1. This is
We don't have Q as not Q.
Yeah, so you can use this. Because since P is true, we'll try to do indirect. So that's why
I don't understand why.
with that should
You did.
that should the hypothesis. And the next one
If
is
not Q, then not Q.
it means it, anything above the line, the hypothesis.
Oh, okay.
That's just you have to put it in there sort of.
But you don't know
And then-
if
If P then Q.
So since P is true, and P leaves Q,
I think
Or list P.
Oh, it is.
yeah, that tells us
Three is
so we know Q must be true.
sort of. P leads to Q means that anytime P is true, Q is true. But if Q is true, P is not necessarily.
I just don't.
I'm gonna
So
do
you've got
not R.
if not Q, then not Q.
To not.
Using detection reasoning, if then Q, therefore. Oh. I was looking at that, I thought that was a logical conclusion. That's why I was really. I'm not saying it's wrong.
We started off right, or we didn't start
Never
off.
mind.
Okay.
I thought that was.
So not R, not Q,
Like we use
and not R.
direct reasoning to get
So if there's direct reasoning, you can say.
Now I'm understanding why it comes about there.
But we know Q is true. So you have a contradiction.
We have not R and not Q.
so we know that Q is true and we know that not Q is true.
Oh.
to outright contradiction.
So do we have to get the P though, or do we?
Well, if we know there's a contradiction when we assume P, then we can assume that not P is true.
So we don't have to get all the way down to getting a contradiction. We can get a contradiction. I think they're the same.
As long as we get that contradiction by assuming P.
I don't know. I don't have it.
Well, and also the
Yeah, and the Mormon. I always have the Mormon. But then I was starting to get involution and null and those.
At this point, you can just say therefore not P.
So that's direct proof. That's a direct proof. This is an indirect proof. The direct proof, you just prove it as.
you just give me hypothesis and you arrive at the conclusion.
That's what you were.
No, I was.
You get the conclusion and then you arrive at the
That's
contradiction.
indirect.
That one you assume the conclusion is true. This one you assume the conclusion is false.
Oh,
Yeah, so you
That's the most
say, okay,
important part.
for this one, P is true, if you're gonna come out right. But
Yeah,
since
right.
these contradict each other, like each other, you know.
And
I assume you will.
I didn't have much space.
Well, we know that it's true. There's not three cases. No, we can just do protection on this.
If it's Friday, you're in class.
So it's basically a five-day steps. All right, first two.
So you gotta form around to make 5 true. You gotta do what's called a counting logic. So if P implies Q, then not Q implies not P.
Still down.
Say not on, because there's always something, right?
That
Or there
lets
is.
us say
I don't really try.
Alright. So just to make me feel good, yeah, go ahead and throw in the reasons for all of
Yeah,
it.
it's still down.
What do you got here?
Indirect and direct.
Alright, direct. Hypothesis. Direct reasoning, hypothesis. If it's on your notes, then yes.
Okay, we get 4 pages.
You got 8 single-sided pages for double.
Wow, that's a little long.
And you can shrink those down to quarter size and still be yours.
Okay.
Yeah, I've never seen that when I was before classes. I made a ton of notes to pass these tests.
We did 8 because 8 should be plenty. You should only need like 2 or 3 pages.
Yeah.
Because
Tons of-
you don't need notes telling you how to do this. You do this enough and you know the
Yeah, you
process,
see the
right?
identity.
But you need to know what is indirect reasoning, what is detachment, right? But most of these are anyway. And one year, a student printed up like a nice note sheet of everything and posted it. And I started reading it, everybody like made the same mistake, the mistake
Yeah,
of the note
typo.
sheet, yeah. Yep. Alright, so P implies Q, you got nothing there for nothing. Okay, so direct. Indirect reasoning P,
Yeah.
Q.
We have color. He's just, it's so weird.
Reasoning implies Q.
You don't need to need it.
So I think your reason for 5 is indirect reasoning.
If I remember, I looked on that one.
Yeah.
It says the same thing.
So indirect reasoning says if P implies Q and you have not Q, then you must have not P. Disjunctive simplification has to do with an or. Right? Disjunct means or. So if you have A or B and B is false, then you know A is true. So yeah, that's perfect logic. Different name for the reason 5 is indirect reasoning. So indirect proof P implies Q, Q.
So the numbers just point to where you're. indirect reasoning.
Q contradiction, therefore not P. Perfect. Good to go.
This is indirect reasoning.
Probably, yes. Did you find multiple ways?
If P implies Q and you have not Q, then you can conclude not P.
Good.
Yeah, you give it down here.
And then that's a 3.
Not even here. That because just because P is false doesn't mean Q can't be true. That's what
That's a contradiction.
that
You
is.
put it down if you want P is true. So then not P is true. So you put down not P.
No, I asked her.
That's a contradiction.
Not.
Yes, this is what I
So you can just or not. That means 4.
Okay.
Yeah, so this or this. Either one is true.
Okay. All right. So that was due at 8 this morning. We'll go ahead and I think they fixed the internet. As soon as we get internet back, I'll email them. They didn't. But I can't email them. Okay, cool. All right. So.
I did the indirect.
Wait, what?
Draw like some
Yeah, no, that's not the part I was asking about. How did it break through? Oh, ow. They were I got the
Because I didn't know it was.
Man,
I didn't know what it was. What is it? Like upside down mouse.
I hated those, like we're getting there.
You had to always be with all those.
So wait, what's the map on?
Wait, what? Oh, this is the.
Yeah, you roll it around.
I just did it. And not
Another day goes to 5. I need this stuff happening.
I tried to do it, and then I realized that I had no idea.
just 2 days ago I and then I got each core
I don't really all the
one rate and I had it.
I could not find any.
Personally, I found this really easy to do because it feels like this is set up. But on the homework, a lot of them it was hard getting at first step. I wasn't sure how to do it. Yeah, and I think it's like giving you the large wisdom model. You're always just looking for one.
Try to install it on my desktop and bring it in again.
Oh, yeah.
It's already different.
It took me like
Actually, that's the first one.
It's like chips and balls, balls in the cup from like SWAT. You know, like I missed the step on the stair right there.
Somebody stuck my hand up. They never turned on, but it actually.
I dropped my watch. Sorry.
well,
My watch band is so weird.
yeah, but does he have like
Oh, so you got our, you also got not our license, process history. Yeah, proved R, right? You don't have to then you can say that's an contradiction, therefore,
They all just like freak out.
all right, so let's go ahead and sit back down. I think this looks great for everybody.
Anywhere, something we can call it.
Yeah.
It's actually kind of difficult to trace down if you're not focused
Yeah. But if
on, especially if you're talking
If they're
about
not
another
careful.
layer of reference.
Okay. All right, so so there's no class on Friday. Everybody know that?
yeah.
Friday's a holiday, right? So it's technically a faculty work day, so I get to come in and do work 2 days a quarter. So so Monday we were talking about divisibility, right? And we were talking about A divides X means there exists some number K such that X is equal to K times A. So there's different ways to say this. A is a factor of X. X is a multiple of A. X is divisible by A divides X. There's lots of terminology, but the idea is if you take X and you divide it by A, you get an integer. Okay, that's the punchline. So A goes into X. So we know that 3 divides 12, because 12 over 3 is an integer 4. But 3 does not divide 11, because 11 over 3 is 3.66. So we can use that divisibility definition. And so you're working on some proofs on the board that said things like theorem. If A divides B, then A divides B times C for all integers C. So I think that was the first one you were working on the board. So if A divides B, then A divides any multiple of B. And to prove something like this, the only thing you have is the definition of divisibility. So how could we do this? You're trying to prove if this is true, then that is true. So we start off by assuming this, and we try to prove that. And then that's precisely what we've proven. If this is true, that is true. So we start off with A divides B. That's a hypothesis. And then I'm just going to use the definition of divisibility and say there exists some number K in the integers such that B is equal to K times A. And that's the definition of divisibility. And I'm going to make a little scratch area called ignore. And I'm going to say, what am I trying to show? I'm trying to show that A divides B times C. So I need to ultimately prove there exists some, D such that BC equals D times A. That's the definition of A divides BC. So I'm going to say, let's show this. I'm not going to say K because I'm already using K down here. And I'm not saying that this has to be the same as this. I'm just saying there has to be some integer, so I'm going to call it D, such that BC is equal to D times A. So that's just using this definition on this statement that A divides BC. And now I'm going to look at what I got and what I'm trying to get to, and you kind of play around. And the first thing that occurs to me is if I multiply both sides by c, my left sides are going to look the same, right? And my right side's not going to be d times a, but d can be any integer. So let's multiply by c. I'm going to say b times c equals k times a times c. And that's just going to be algebra. And now I'm going to rearrange things over here because I'm trying to show that BC is equal to something, integer times A. So I'm going to move the A to the outside, so this is equal to K times C times A. And I'm going to throw in some parentheses. And that's algebra. And I'm going to note that KC is an integer, because k was an integer, and we've been told c is an integer, right? And so properties of integers, so this is step 5, kc is an integer. Well, I've just shown that b times c is equal to an integer times a, and that's the definition of divisibility. So I can say, therefore, A divides B times C. And that's the definition of divisibility. And that's what I wanted to show. Now, the first times you're trying to do this, it's not that straightforward, right? But try some examples. Put in actual numbers. Set A equal to 3, set B equal to 90. And 3 divides 90. Okay, well, suppose I multiply 90 by 7. So let's do this. Let's suppose A divides B. Show that A divides B times C. So let's say A equals 3, B equals 90, C equals 7. So what is this theorem claiming? Well, if 3 divides 90, which it does, right? 90 is 3 times 30. This is claiming that 3 divides 90 times 7. Well, if I know that 3 divides 90, I kind of automatically know that 3 divides 90 times 7, right? When I say 3 divides 90, that's a consequence of the fact that 90 equals 3 times 30. And I can plug that in here and say 90 times 7 is equal to 3 times 30 times 7. And if I just put these together, that's how I can see that 3 divides this thing. And that's really what's going on in here, right? But if you work with particular numbers, it may be a little easier to sort of see what's going on. And you do this with a few different cases, and eventually it will probably jump out at you that all you're doing is you're taking the fact that 3 divides 90. To write 90 as 3 times something, and now you can take 90 times something else as just that something times something else, and your 3 still comes out. And for me, that's kind of the path that leads to how you generalize it into something like this. But it's not an exact science, right? It's something that just takes practice. And you may come out of 215 and still feel kind of icky about proofs. That's okay. It's different for everyone, sort of where this kicks in and how it kicks in. And it's absolutely different how it ends up being coded in your brain that makes sense, right? So we can't just transplant neural pathways. But it will eventually make sense, right, at some point in your career. But it's a puzzle, basically. You experiment with it and you play around with it, and eventually some of these things will be automatic, right? Some of them may take some head scratching. Some of them may just be like, I don't think I can do this one. And that's okay, right? You got your whole life to figure out proofs. So let's do a different one. So here's another theorem. If A divides B and A also divides C, then I claim A divides 5 times B plus 7 times C. And the 5 and 7 should tell you that those numbers probably aren't important. They probably could be any numbers, which can help you think about directions. So I'll start this, and I'll say A divides B, that's a hypothesis. And then I'll say there exists some K1 such that B equals A times K1. That's the definition of divisibility. And I'll do A divides C, that's a hypothesis. And I'll say there exists a K2, these are integers, such that C equals A times K2. And that's the definition of divisibility. And so I've got two potentially useful things I've written. I know I can write B as A times K1, and I know I can write C as A times K2, where those K's are integers. And over here is my purple ignore area. And over here I'm going to note that what I'm trying to do is show that A divides 5B plus 7C. So show that 5B plus 7C equals A times, I'll just call it some big K, where K is an integer. And so now you sit back and you stare. I know those two things that are boxed in red. I'm trying to show this thing over on the right in my ignore section. Trying to show 5B plus 7C is some multiple of A. So how could I try to combine those into something different?
Replace B and C with A times K1 and A times K2.
Let's just try replacement. Partially because there's not a whole lot else to try, right? So if you see something that you can do, give it a shot. I'm not going to use this statement anywhere in my proof though. Okay, this is my ignore section. I am absolutely not going to write 5B plus 7C equals A times K. If I do that, you get the frowny face. Okay, we haven't proven this. But I can totally do this. And nobody can argue with that. Why? Because I already know that B is equal to this and C is equal to this. And all I've done is substitute those versions of B and C into this expression. I don't have to justify why I did this. Why did you write 5B plus 7C equals something? Because I wanted to. That's the only reason you need it. It's your proof, right? But the reason that this is true is just substitution. But once you write that down, you can maybe see what's happening here, which is I've got an A here and I've got an A there on the right side in both of these expressions. And I'm trying to get 5B plus 7C equals A times something. Well, there's an A and there's an A. Let's factor it out. So let's do some algebra. I'm not going to touch the left side, but I'm going to pull out this A.
Couldn't you just say that 5K1 plus 7K2 is just any integer? Or
It's not any integer, but it is an integer. Because K1 is not any integer, right? We said there exists a particular K1 which makes this true. But we can observe 5K1 plus 7K2 is an integer. And that's just how integers work. Because K1 and K2 are integers. We said that in steps 2 and 4. And now you're pretty much done, but you still need to say this. 5b plus 7c is equal to a times an integer. That's the definition of a divides 5b plus 7c. That's the definition of divisibility. And that's what we were trying to show. That's the conclusion. So there we can say QED. So you can make up problems like this, right, pretty easily. You can find problems like this in the book. There's other textbooks on Canvas, by the way, that do a better job of number theory. I think the current textbook, the one that's the main textbook for this course, doesn't do number theory the way I like. But let me dig through that book and post some sample problems. But you can make problems up like this, right? We could show that a divides b minus c if a divides b and a divides c, or a divides b times c, or things like that. And they're all going to kind of be the same style of proof, right? Basically use the definition of divisibility to make some statement about the stuff that you know. Figure out what you're trying to show. Try to rewrite some piece of that by substituting in these definitions, and then try to rework it into this full statement of divisibility over here on the right. And I'll warn you, it's possible that when you get here to the end, you actually end up completing your proof. You have no idea how you did it. Okay, that happens a lot in math. And it can be disconcerting, but it's also kind of cool when you can actually prove something and convince yourself it's true, but not really understand why it's true. That's sort of cool in its own way. It's a little disturbing in a bigger way, for me at least. But that means that there's like something you know how to do, but you haven't really sort of conceptualized it yet. And when you do that conceptualization, that's power. All right, I'll try to post some sample problems from one of the texts. So questions about that? So let's go on and look at what divisibility is good for. Did the lecture talk at all about modular systems?
Yeah.
A is congruent to B. Okay, so let's rehash that. So this is a working definition for when we say this thing on the top, and this thing reads as A is congruent to B modulo M. So this triple line is no longer logical equivalence in this chapter, it's congruence. Okay, so A is congruent to B modulo M. And this means roughly A divided by M and B divided by M have the same remainder. But that's not an exact definition. We'll see why shortly. But if you don't go too crazy, right? 17 divided by 3 is what? 5 with a remainder of 2. Because 5 goes in 5 times, that gets you to 15. You got 2 left over, gets you to 17. All right, 23 divided by 3 is what? Seven gets you to 21. What's the remainder? Remainder of 2. So same remainder. That's all you need to say 17 is congruent to 23 modulo 3. Right, so this is the 17. And And this is the 23. And the thing you're dividing by, that's the modulo. So A is congruent to B mod M means A and B have the same remainder when you divide by M. There's a bit of imprecision in this definition though, because I asked you what 17 divided by 3 is, and Alex said it's 5 with a remainder of 2. But you could also have claimed that it's 4 with a remainder of 5. Because 3 times 4 is 12, and then you got 5 left over.
Remainder has to be a number that is less than the dividing.
Exactly. So we're going to insist that this remainder is something between 0 and this number minus 1. Right? But technically this is correct, but so is this. 17 divided by 3 is 0 with a remainder of 17. That's certainly true. Because 3 times 0 is 0 and you got 17 left over. And it gets worse. It could be -1 with a remainder of 20. Because 3 times -1 is -3, and you've got 20 left over to get you to 17.
Could also be a 6 with a remainder of -1.
Yes, could be a 6 with a remainder of -1. Because 3 times 6 is 18, and you've got -1 left over. So we can have all kinds of crazy fun. But we don't want to do that because we're in school. So here's what we're going to do. I don't want to do that. The remainder of A divided by B must be bigger than or equal to 0 and less than B. So we're always going to insist when we talk about remainders that it's a number in that range. Which is usually what we would mean when we say that anyway. So if I do 28 divided by 5, that goes in 5 times with 3 left over. And 3 as a remainder, it's bigger than or equal to 0, it's less than 5, that's a good remainder. So there's a theorem, it's actually called the division algorithm, it doesn't have the word theorem in it. It's called the division algorithm, and it claims that there's always one and only one such remainder that satisfies this property. So we can talk about the remainder of A divided by B, and it's well defined and it's unique. Well, here's what we're going to do. How many integers are there?
Infinite?
Infinite number of them. That's a lot, right? We're going to simplify some of our problems by, instead of talking about remainders, instead of talking about integers, talking about remainders when we divide integers by something. For example, $4,735,617 modulo 10. So what's the remainder we get if we divide this number by 10? It's a 7, right? We know that because that's how 10s work. It's just going to be that last digit. So this is congruent to 7. Okay, and I'll make my life a little crazy. 2,143,286 is congruent to what mod 10? 6 mod 10. Okay, suppose I want to know what this number plus this number is congruent to mod 10. I can add these together. And what is this congruent to mod 10? But what is 7 plus 6 congruent to mod 10? What's 7 plus 6? Okay, we got that. So what's 13 congruent to mod 10? That's 3. Those are the same. And that's not just a coincidence. That's always going to happen. So here's where we're heading with this. We can do things like addition, subtraction, multiplication on integers, and then ask what that final answer is congruent to modulo anything. Or we can take those integers, see what each of them is congruent to modulo something, and then do addition, subtraction, multiplication on those modular equivalences. And we'll always get the same answer. And this is really powerful, because these numbers could be really huge and multiplying them together could be a real nightmare, right? But if I want to know what this times this is congruent to mod 10, it's congruent to 7 times 6 is 42, it's congruent to 2. Guaranteed. And that's not so impressive to us, because if we started to multiply these out, 7 times 6 is 42, and there's a 4, and we'd start doing this, but we know that like nothing else is going to change this digit. Okay, but that's because we're working mod 10. So suppose we're working some other modulo, like 7001 and I don't know, 725. And let's work mod 7, and let's multiply these. So what is 7001 divided by 7? What's your remainder? It's just 1, because I picked 7001 because it's 7,000 times 1, or 7 times 1,000 plus 1. So 7001 is congruent to 1, modulo 7. And 725 you got to work a little harder on. But 725 divided by 7, that goes in 1. You get a 25, that goes in 0. You get a 25, and 7 times 3, it's 21, and it looks like you got 4 left over. So 725 is congruent to 4, mod 7. And so this product is guaranteed to be congruent to 4 mod 7. So 7001 times 725 is that big, long, horrible number. And that big, long, horrible number divided by 7 is this thing. But if I do that big, long, horrible number, well, let's do this. Let's just do 725,103 times 7, and that's 507,5721, and we add 4 more to get to our original number. So it's got a remainder of 4. I wonder if I can actually do modulo in here. Nope. Didn't think so. So, like I say, the punchline here is that we can work with integers and then reduce modulo something, or we can reduce our integers and then just use those reduced very small numbers, which are going to be, in this case, between 0 and 6, and find our answer. All right, so this works with addition, it works with subtraction, it works with multiplication. Division is a different story, because division of integers is kind of weird. That's why we have rational numbers. That's why we end up with real numbers eventually, so we can define division. But if we say something like 5 divided by 2, and what is that congruent to mod 7, it doesn't really make sense, because 5 divided by 2 is not an integer. So we got to be a little careful with division. Anybody here taking linear algebra? Already took it? Okay, so same idea with matrices. Some matrices you can invert, some you can't. Some integers you can find an inverse of, some you can't. Which ones are invertible? It's going to be the ones that you're working modulo a prime. That's a different story, but we'll get there. Well, what can we do with this? So here's 3 to the 17th. It's a big long number, 12 million something. 129,140,163. And suppose we want to know what the remainder is when we divide that by 7. So we want to find 3 to the 17th modulo 7. Why do we want to find this? This is going to be the key to making crypto systems work. Being able to do these kinds of calculations efficiently. And when we talk about public key systems, it's going to be a bunch of modular expressions like this. But they're going to be huge numbers with like hundreds of digits. So how can we find 3 to the 17th mod 7? Well, here's a trick we can do. This is called modular exponentiation. So 3 is congruent to 3 mod 7. Everything's congruent to itself, right? So 3 squared is just 3 times 3. That's congruent to 3 squared. Well, what is 3 squared? It's 9. And what is 9 congruent to mod 7? That's congruent to 2. I'm not going to keep writing mod 7. This is all going to be mod 7. So 3 squared is congruent to 2. What about 3 to the 4th? But I don't want to multiply. I'm going to be lazy. Now I know 3 squared is congruent to 2, and this is just 3 squared times 3 squared. This should be congruent to 2 squared, which is 4. And 3 to the 8th is going to be congruent to 4 squared, which is 16. And 16 is congruent to what mod 7? That's congruent to 2. I'll write down a 16. That's congruent to 2. But now I got a pattern. I can do this all day now. 3 to the 16th is congruent to 2 squared, which is 4. And if I wanted to keep going, 3 to the 32nd will be congruent to 2, 3 to the 64th will be congruent to 4, and so on and so forth. So let's try 3 to the 64th. So there's 3 to the 64th. Let's do 3 to the 64th minus 4.
You did the 63rd.
Oh no, I broke everything. There's 3 to the 64th, thank you. 3 to the 64th minus 4 is this. And this thing divided by 7 is an integer. So 3 to the 64th was 4 more than a multiple of 7. Now my original question was 3 to the 17th. There's a trick we can do here. If I write 17 in binary, what does this mean? This is 2 to the 0. This is 2 to the 4. So 17 is 16 plus 1. Well, that's useful because this means 3 to the 17th. Bless you. 3 to the 17th is 3 to the 16th plus 1. And if you remember how exponents work, this is 3 to the 16th times 3 to the 1st. Well, I've already discovered that 3 to the 16th is congruent to 4, and 3 to the 1st is congruent to 3. So this is congruent to 4 times 3, which is 12, which is congruent to 5 mod 7. And 3 to any number, right? I can write that number as a sum of powers of 2, and I know what 3 to each of those powers of 2 is, right? And I've got a pattern here. This is just 2, 4, 2, 4, 2, 4 forever on. So I can very quickly find out what 3 to the 16th and 3 to the 4th and 3 to the 128th is, and multiply those out. First, 3 to the 17th should be 5 more than a multiple of 7. So 3 to the 17th minus 5 is that number, and that number is 7 times an integer. So working in a modular system is really, really useful. Okay, it lets us take problems that would normally be pretty complex, like finding 3 to the 64th, and it lets us reduce them to pretty simple calculations. So when I was a kid, I was like a geek about prime numbers. And I was always sure that I had a way to generate prime numbers, because we don't have such a way yet. We'll talk about primes next. Do you know what prime numbers are? You use them in 121 and 120, right? The numbers without factors.
5, 7, not 9.
Not 9.
11.
13.
Yeah. So the numbers that have no factors other than the obvious ones, which is the number itself and 1. So I was always looking for a formula to generate primes, because someone told me that I couldn't do that. And I come up with a formula, and I found somehow this math professor at University of Illinois, and I started sending him notes. I was like 12 years old. Started sending him letters saying, I believe I have discovered a formula, blah, blah, blah. And he'd send back, how my number was factorable and wasn't prime. And about the third time this happened, he sent me something like this. It was from a printing calculator. And it was just a bunch of simple calculations, but he was able to test this big, huge number I had sent him that was basically too big for me to find a divisor. And he showed me how to find a divisor with it, and it was just using modular arithmetic, and blew my brain. I thought it was really cool. This person did this for some 12-year-old punk. All right, so what can we do with this? Let me give you another example. So is this number divisible by 3?
It's hard to tell from here.
Yes.
Who said yes? Why is it divisible by 3?
Isn't there a rule with that if the last 2 digits added together are divisible by 3, then the whole thing is? Some rule.
Some rule like that, but that's not true, because
I don't know what the exact rule is.
0 and 0 add up to something divisible by 3.
If all of the numbers add up.
If all the numbers add up to something divisible by 3. So 4 and 2 is 6, 11, 18, 21, 30, plus 0, 30 is divisible by 3. That's divisible by 3. Why does that work? Math. Perfect answer, actually. So what is this thing? This is a big, long-winded way of saying 0 plus 9 times 10 to the first, and I'm going to write 0 as 10 to the 0, plus 3 times 10 squared, plus 7 times 10 to the fourth, and so on. All right, that's what we mean when we write a bunch of digits side by side. It's each successive digit multiplied by the next higher power of 10. So what is 10 congruent to mod 3? And 10 to the 0 is 1. What's 1 congruent to mod 3? That's just 1. 10 squared is going to be congruent to 1 times 1, which is 1, right? 100 is 1 more than a multiple of 3. And 10 cubed is going to be congruent to 10 squared times 10, which is 1 times 1, which is again 1, mod 3. And every power of 10 is 1 more than a multiple of 3. Which means this expression up here is congruent to 7 times, 10 to the fourth is congruent to 1, plus 3 times 10 squared. I skipped a number somewhere. It should have been cubed. 10 squared is congruent to 1, so this is 3 times 1. 10 to the first is congruent to 1, so that's 9 times 1. 10 to the 0 is congruent to 1. So this number is congruent to just the sum of the digits, mod 3. So if you add up the digits and the sum is divisible by 3, the original number was divisible by 3. So that kind of works automatically. And you can start going a little crazy with this. If you work mod 9, 1 is congruent to 1, 10 is congruent to 1, 100 is congruent to 10 squared, which is 1 squared. 1,000 is congruent to 10 cubed, which is 1 cubed, and so on. And you got the same situation. So if the sum of your digits is divisible by 9, your original number is divisible by 9. And that's pretty cool. What about mod 11? So what is 1 congruent to? Just 1. I'll do that one for you. What is 10 congruent to mod 11? 10. But I'm going to cheat and say that's also congruent to minus 1. Well, it's not the definition of a remainder. So I said remainders have to be between 0 and this thing minus 1. But this is saying that 10 and minus 1 have the same remainder when you divide by 11. And minus 1 divided by 11 is ten with a remainder. I suppose we say it's 1, right? That's got a remainder of, sorry. So minus 1,
Well, it's either be 0 or remainder is -1.
so it could be 0 with a remainder of negative 1, right? And what else could it be? Because we're going to want to find a remainder between 0 and 10.
That would
Negative 1 for remainder of 10.
Negative 1 with a remainder of 10. Because if we take 11 and we multiply by negative 1, we get negative 11. And if we add a remainder of 10, that gets us to negative 1. So negative 1 over 11, the remainder that we would say we get when we do that division is 10. Because that's between 0 and 10. And so this and 10 over 11 is just 0 with a remainder of 10. They have the same remainder, so they're congruent. But this is a useful way to look at this, because what's 10 squared congruent to? Negative 1 squared, which is just 1. 10 cubed is going to be congruent to 10 squared times 10. That's 1 times negative 1. That's negative 1. And so on. We've got a pattern. Well, punchline, if you take that pattern and you plug it into this thing that we were doing over here, and you want to find what this number is congruent to modulo 11, it's the sum of the odd digits minus the sum of the even digits. And I'm not going to do that because we're kind of going down a rabbit hole. But if you plug these in for the powers of 10, right, this is going to be plus 1, minus 1, plus 1, minus 1. The sum of all these digits, which is this number, the sum of all these terms, which is this number, is the sum of the positives minus the sum of the odds minus the sum of the evens. So take a number like 11 times 234, and you get 2574. So this adds up to 9, this adds up to 9. The difference is 0. That's a multiple of 11, so this is divisible by 11. And if you do some crazy number, like 7989, 4353. All right, so the odd digits and the even digits. So the odd digits, 3 plus 3 is 6. Oh, yeah, that would help. Thanks. So there's our crazy number. So the odd digits are 3, 3, 9, and 9. the odd position, so 3 and 3 is 6, plus 9 is 15, plus 9 is 24. And the even positions, 5 and 4 is 9, plus 8 is 17, plus 7, well, that actually came out exactly the same. So again, 24 minus 24 is 0, multiple of 11. So these are just little games you can play, right? But they come from this fact that we can take this big, long expression, which is adding bigger and bigger powers of 10, and instead of adding all of those up and dividing by 11 or 9 or 3, right, we can write each of these powers of 10 in terms of its remainder when you divide by whatever we're dividing by, and then just add up those simpler expressions. So this is a general theme with modular arithmetic, right? Infinite number of integers, very, very small number of modular equivalences. If we're working mod 7, every integer is congruent to one of 7 things. And if we can do our arithmetic on those 7 things, and we can because they're all small, they're all between 0 and 6, right? We can avoid working on these arbitrarily big numbers. And so in cryptography, we're going to take messages, we're going to translate them into big, long integers. We're going to take 100 letters, we're going to use 2 digits for each letter, and we're going to end up with a 200-digit integer. And we're going to try to do things like raise that to powers and divide by numbers, but we're going to reduce modulo something first. And this is going to be tractable by a computer. And our computers do this all the time. Anytime we do anything with a secure connection. All right, we got 8 minutes left. Let me mention divisibility. And then before Monday's class, I'm going to post some homework questions related to this stuff. And Monday we'll spend working on this stuff in groups. Let me mention something about dividing. So let's make a table of multiplication mod 4. And in school, we multiply numbers, we make a multiplication table, right? So you list one number and another, and you show what you get when you multiply, and you have to memorize that, and there's great pressure and stuff, right? And that shows us how to multiply small numbers, but it doesn't tell us how to multiply 245 times 76. We got to learn tricks. Modular systems, that little multiplication table gives us everything we need to know, because mod 4, we've only got 4 numbers to deal with, 0, 1, 2, and 3, right? That's the beauty of mod systems. How big do they make you memorize multiplication tables in school?
12.
12 by 12? Okay. I think that's what it was for us. So we're going to do multiplication. And I'm just going to do this quickly because we're running towards the end of the class.
Why is there a 0?
3 times 2 is 4, so 4 mod 4 is 0.
Yeah.
Modules.
All right, so that's mod 4. Let's look at mod 5. So these are all zeros. And you can trust me on these, I think, but I could be wrong. There's something fundamentally different about this table versus that table, besides the fact that one's mod 4 and one is mod 5. And let's ignore everything in column 0 and row 0. And what's a difference that jumps out about this piece versus this piece?
All the center.
There is no center of the mod 5, though.
There's no center, which has to do with the size because it's even.
Yeah.
But what else do you notice?
It counts up or down.
It counts up or down.
Yeah, that's the same.
What
It's
else?
just the 0 versus 4, 1, 1, 4.
There's a 0 over here. What is this 0 saying? This is saying 2 times 2 gets you 0. That's a little weird. Does that happen in regular algebra? All right, regular algebra, we say if a times b equals 0, either a is 0 or b is 0. Well, that's not 0 and that's not 0. But when you multiply them, you get 0. A little bit weird. Say what?
It's because there's no remainder?
Yeah, because there's no remainder, because 2 times 2 is divisible by 4.
They're all remainders.
But over here, there's no zeros.
And that's because one's even, one's odd.
Say again? That's because 5 is prime. Primes change everything. If you make this table for any prime number, you get no zeros over here. If you make it for anything that's not a prime, you do get zeros over here. When we have zeros, our arithmetic totally changes. Because we're used to saying if a times b equals 0, then a equals 0 or b equals 0, or maybe both, right? That's how we solve equations. We can't do that modulo something that's not prime. Because here's a counterexample, right? Product is 0, but neither of the things we multiplied was. But over here, the only time that the product of two things is 0 is if one of them or the other one is 0. And that turns out to be the key to being able to define division, right? And we can't define division here because it would lead us to conclude that like 0 divided by 2 is equal to 2, right? Because I divide both sides by 2, but we also know 0 divided by 2 is equal to 0. It's not well defined. But over here we can make a very well defined notion of addition. And it comes down to this idea that the modulo we're working with is prime. So I may try and post some lectures for next week because I think we're at a point where I can go back to some short lectures. But the next topic is going to be basically prime numbers, and we'll tie that into modular systems. But Monday we'll spend some time on the board. I'll post some homework questions, and we'll work on these principles of doing modular arithmetic. And then we'll go on. We'll talk about primes. We'll talk about open problems, and then we'll get into applications, and we'll conclude with cryptography and public key crypto.